Good day, everyone. I am Aziz Radwan from Case Western Reserve University. Our paper is titled An Inkjet-Printed Silver Strain Gauge on Flexible Cellophane Using a Metal Salt-Based Ink. The co-authors are Dr. Yongkun from the University of Colorado, Boulder, and Dr. Christian Zorman from Case Western Reserve University. Our agenda is as follows. First, I'm going to introduce the topic. Then I'll present some relevant recent works on silver nanoparticle strain gauge. Following this, I'm going to demonstrate how we fabricated our strain gauge, how benchtop testing was carried out, and finally, results and discussion. To begin with, I'm going to shed the light on the types of conductive inks, the commonly used flexible substrate, and the ink sintering method. Starting with conductive inks, what are the common types of conductive inks? They can be categorized into polymer ink, carbon ink, metal organic decomposition ink, particle ink, and particle-free ink. Now, in the interest of time, I won't be able to go over each ink type, but I will shed the light on the last two, particle ink and particle-free ink. Particle ink is normally not easy to make. They require some expertise, and in order for them to be sintered, they require high temperature. And because they have particles, even at the nano size, they can still cause some nozzle clogging. As for the particle-free ink, they are easy to make. That's the ink type that we used. We made it in the lab. And because they are particle-free, then there is no agglomeration or sedimentation issue. In addition to that, they're compatible with various substrates. Speaking of substrates, what are the common flexible substrates used in inkjet printing? We have PET, polyamide, PDMS, PVA, and PCA. The first three are thermally stable. They can withstand high temperature, so there are no issue. If you want to print a metallic ink on this substrate, and then you want to cure them at high temperature, they can withstand high temperature. But as for the VA and PCA, they have a low melting point, below 200 degrees Celsius. So high temperature annealing will not work on these substrate if you are to sinter them. What are the ink sintering methods? Very quickly, you have thermal sintering, medium to high temperature, takes an hour or two. You have electrical sintering, it's done at room temperature, but takes seconds, that's faster than thermal. There's even faster than electrical, which is the laser sintering. And it utilizes transient localized heating. And this laser sintering takes a fraction of a second. The last one is plasma reduction. This is the ink sintering method that we use in our work. Plasma reduction is a low temperature, below 100 degrees Celsius, and it takes minutes. That's the introduction. Let's move on to the objective of our paper. The objective is to fabricate silver-based strain gauges using low temperature plasma reduction technique. And we're also going to investigate the effect of argon plasma reduction time on gauge factor. Here in this table, it lists a summary of recent works on silver nanoparticle ink. And there is I'm making this comparison because silver nanoparticle has been widely used in making temperature sensor or strain gauges. So if you look at this table, it's sorted on the gauge factor value from lowest to highest. The highest one is done by Jew group, had a gauge factor of equal to 8. while in our work, we report a gauge factor equal to 6. That's the second highest in this comparison, while the other works have a gauge factor from 1 to 3. The common substrate used were polyamide, polyurethane, PDMS, polyimide, and Teslin. But if you look at the substrate temperature, that you will see all of them use medium to high temperature, at least 100 degrees Celsius, or 10 minutes to 1 hour. And that is called the curing time varies depending on the structure and the particle size. While for our work, our substrate temperature during sintering was much less than 100 degrees Celsius. It was 55 degrees Celsius, and we printed our silver ink on cellophane. Speaking of cellophane, why did we choose cellophane or Scotch tape? Scotch tape is a cellophane material. One adhesive side at the bottom has a thickness of 60 micron. And one advantage of a cellophane tape is it is very flexible and also sufficiently hydrophobic. We tested the silver ink contact angle, which was about 50 degrees, and thirdly has good printing fidelities. We printed a couple of structures, meandering structure, and they have good printing fidelity. So before we print a strain gauge on the cellophane tape, we had to test its elastic limit. How do we do that? We brought Scotch tape onto a tensile tester. We double clamped it, and this sample you see has a length of 7 centimeters and the width of 19 millimeters, or nearly 1 inch. And using a force gauge and the LabVIEW software, we plotted the stress strain curve, as you see in this curve. So this curve tells us what is the elastic limit of a Scotch tape, and you see it's very soft. The Young's modulus is 3.86 gigapascal, and the elastic region is nearly 1.25%. So now with this plot, we know if we are to test or stretch a strain gauge, we shouldn't exceed 1%, and that's what we did, as you will see shortly. How did we make our ink? We brought 1.7 gram of silver nitride. We mixed that with ethylene glycol, deionized water. We stirred them for 15 minutes, and we poured that into a vial. We let this off for 24 hours. After 24 hours, we loaded that ink into a printer cartridge. We set the printer temperature at 50 degrees Celsius, and immediately after printed, we put it into a vacuum chamber supplied by RF generator and fed by argon gas line and nitrogen gas line for purging. And in this step called plasma conversion, we reduced plasma. We used plasma to reduce silver salts into silver over a temperature range from 40 to 65 degrees Celsius. This is a picture of the converted silver ink samples. So very briefly, if you want to know what really happens during plasma reduction, here's you have a plasma and a substrate. We put our silver ink sample, silver, which is silver nitride dissolved in ethylene glycol. First you have the silver nitride, they're ionically bonded, and then first they recrystallize, and with the argon plasma, it's an ionized gas. The argon plasma hits the silver nitride, and that will cause ionic bond dissociation, in other words, plasma reduction. With the addition of electrons, the nitride evaporates, leaving ionized silver atoms behind. And with the generation of secondary electrons, the silver atoms nucleate and center. The longer the plasma exposure time, the greater the nucleation and plasma centering. So here are the results. The picture on the right-hand side shows you a sample of the strain gauge. And here on the left-hand side, you have a plot of resistance versus plasma duration from 5 minutes to 30 minutes. At 5 minutes, the resistance was 1600 ohms. At 30 minutes was nearly 100 ohms. And you see that the resistance decreased exponentially from 1600 to 100 ohms. So after we plotted this, we know the longer the plasma exposure, the greater the conductivity. And then we wonder, why shouldn't we test the gauge factor at each plasma duration, what will we get? This is what we got. Here you have a curve, normalized change in resistance versus strain. The plot on the right-hand side is merely the slope of this curve, which is the gauge factor. So the gauge factor here at 5 minutes equal to 6, decreased exponentially, as was the case with resistance, and you see it plateaued after 20 minutes. So you may ask a question, what's the science behind that? Why did the gauge factor decrease as we increase plasma exposure? For shorter plasma exposure, you have thin silver film. When you have a thin conductive film, you do increase electron scattering. That contributes to the total resistivity of your sample. You get a higher resistivity. Higher resistivity means when you stretch the sample, you'll get a higher delta R, and that translates into a higher gauge factor. For longer plasma exposure, you thicken the silver layer or film, which will reduce electron scattering, which means lower resistivity, lower delta R as you stretch the sample, and then translates into a smaller GF. So that's what we think the science behind the decrease of the gauge factor. It comes another question, what about cyclic testing? What is the repeatability of your device? We tested a 15-minute device, as you see here in this plot, and you saw the resistance varied from 490 to 515, and the burn-in period was from cycle 1 to cycle 6, after which it began to stabilize from 515 to 504, 403. So we could claim that the strain gauge printed on cellophane tapes is repeatable. But for further process development, it could be used also as a prototype. In conclusion, I have to say the highest gauge factor we obtained was at 5 minutes when the sintering temperature was at 40 degrees Celsius, about 6. The gauge factor is tunable over plasma exposure from 1 to 6. And since we did cyclic testing, we showed that our sample showed good repeatability over 20 cycles. This concludes my presentation. Thank you for listening.